Sorry about that. Okay, so let's get started here. Just a couple of reminders up there that the reading exercise E1 I extended so you could do it all the way up through tonight. Just give a little extra time for that. The other things here, don't forget that assignments C and D. Those are the unit assignments, the unit comprehension assignments for those units. Those are due Wednesday, February 15th, so tomorrow. There is a grace period with them. And then there is a midterm review assignment that will pop up and become available Thursday. That's the one that you can take as many times as you want. It counts as a unit comprehension assignment. It's a little bit more points than a standard unit comprehension assignment. It takes the highest score, so there's no penalty to taking it more times if you like more practice. Basically, I've set it up so that it samples a couple of questions from all of the other units every time you take it. So when you take it, it will look like a different quiz each time, but then that gives you a chance to practice all those previous ones. So it's randomly samples from those. Again, highest score is taken, a few extra points. That becomes it's not available right now because I want to make sure you get these other assignments in because those will be some of the ones it samples from. So once those sort of disappear, it becomes available and it'll be due next week. It's due basically before the midterm review lecture on Tuesday. So basically the stage one will be a week from this Thursday, so not this upcoming Thursday, a week from it. And so we'll have a review a week from today. And so I don't have anything special planned for that review. I can go over kind of what I think the kind of the greatest hits of the 5 units, just to sort of generate questions. And then I can answer questions, we can work problems, those sorts of things. So bring your questions, and so that's the big reason I'm trying to make this assignment due before that, is I'm hoping it will generate questions that you can bring to class. And then, like I said, midterm stage 1 is Thursday of next week. That will be, if you want to come to class to take it, that's fine, but bring a laptop because it's online. Otherwise, I'll make it available. I'll either make it available Thursday, Friday, and Saturday, or like Wednesday, Thursday, and Friday. It kind of depends on if I'm comfortable with it and have the exam finalized. But definitely available for a couple of days. And so during that availability window, you'll be able to start it anytime you want. You'll use lockdown browser for it, and you'll get 90 minutes to complete it. So it'll be designed to fit within a period, like a 75-minute class period, but I give you a couple extra minutes just in case there's some technical glitches or something like that. But if you come to class, because this class that comes right after here, we'll have to cut it off right at 75 minutes. But the exam will be designed for most people to complete in a half hour, some maybe an hour. I think very few people will need to take the whole 75 minutes. So it's not something that is supposed to make you sweat for the whole period. So that will be the individual portion, and then the week after that on Tuesday will be the group-based portion, where again you can come to class, you can work on it together as a group, or you can do it at home or elsewhere. You can work with anyone who's currently enrolled in this class. You can use any resources that I've provided you, including the textbooks, anything on campus. And that's it. So any questions? Yeah.
There be an assignment E.
No, assignment E is sort of folded up into this C1. So I didn't want to have a review assignment and assignment E simultaneously. So E content will be on this review assignment.
So are the exams the exact same questions?
Yes, so in the stage 2 exam, you'll take exactly the same exam for stage 2, but it won't be with lockdown. You'll get the entire availability window. You can come back to it, later. If you submit it, you can submit another one. After that, it'll take your latest submission. So basically you'll take the individual exam, and you'll be able to use a couple of scratch paper that you can write down what were kind of the difficult problems for you. And then over the weekend, you can kind of think about those problems. So then on Tuesday for the group-based exam, you can say, hey, I really still having trouble understanding this one. Does anybody else have any, ideas about that one? And then you can sort of say, yeah, okay, I always had trouble with that, or I figured out this one was this, and then you can work together. So you'll get the exact same questions for stage 2, but you'll be able to use your shared experience individually on stage 1 to benefit you for stage 2. But if you don't want to work in a group for stage 2, that's fine too. You can do it. It basically gives you a second shot at that exam, but your open book, group available score will only be 20% of your midterm. Your individual score will be 80%.
Do we know how we scored on that first?
No, I won't give you your scores or the answers in between. But once stage 2 is available, when there disappears, then you'll be able to get your scores and all the answers. So it's part of the fun of the game, I guess, is that you sort of try to figure out how well you did from stage 1 to help you figure out what your strategy will be for stage 2.
I have one. So neither of them we technically have to be here for?
That's right.
Okay.
That's right. So yeah, ever since COVID started to do these kind of flexible exams, and it's kind of in the pattern that if you want to come here, I will be here for those periods. If I come here and nobody's here for like 15 minutes, I might leave. But I will be here in case you do want to take it in the classroom, and I'm just basically here to take care of the classroom and do proctoring type things. But for stage 2, everybody's talking to each other anyway. There's not really a proctor, so I'm really just here, just sort of holding on to the classroom. So if you want to come to the classroom, you can, but it's going to be very flexible. Like I said, I'm going to give you more than a day. You'll have at least all day Thursday for stage 1 and at least all day Tuesday for stage 2. But I like to give you a little bit more time than that, so you can kind of plan around whatever. And once I finish making the exam, I'll fix those availability windows. But I like to shoot for 2 to 3 days of availability for both of them. Any other questions? Great. All right. So the information, chapter 3 from Melanie Mitchell's book here. Any reflections on the chapter? Any questions or comments? Things that you definitely want, or things that you thought were interesting, things that you didn't understand. Yeah.
Okay, I asked it in the perusal too, but so it talks about how heat is like sort of the final form for something of energy, how eventually all energy is converted into heat. And I don't understand how, like, this is kind of, I don't know if this is a silly question, but how come the universe isn't just like insanely hot everywhere? Right. If heat is like the final form, when did eventually, it's billions of years old by now.
That's a good question. So we use this term about heat loss, and it does seem a little funny. Like it seems like things are getting hotter. In fact, a lot of times, and we'll get into this, but not the specific part of it, but a lot of cosmologists believe that the end of the universe is something referred to as heat death. That if you actually follow entropy maximization across the universe, you actually lead to a state where there's no movement, where you actually get rid of all the heat. So that seems like counterintuitive. So maybe that's a good way to start, is to kind of think about like, what is this whole second law stuff? And because it does make it sound like things are getting hotter, but really what they're saying is that if you're exerting energy to do work, there's always going to be some fraction of that energy that won't be converted into useful work, that'll be converted into waste. And that waste would increase the disorder of you and the thing that you're moving on. So, if I move an object across the floor, I have put a lot of, energy has been transferred. I ate a muffin this morning and it was stored in me, and then it now gave me enough potential energy to turn into kinetic energy to to move this object. But simultaneously, as I'm moving that object, the object's getting heated up. My hands might be getting heated up. And so there are these extra, things that are getting heated up, but really the important thing is not so much that they're getting hotter, but that energy that could have been used to move the box a little bit farther is instead being used to change how ordered the molecules in my hand are and how ordered the molecules in the box are. So that's kind of the big thing, is that there's always some effort that is lost by converting things into this disorder. And we can actually, maybe to make that a little bit clearer here, it's kind of like this example of like, if I have, I might get more formal on this in a second, but if I have like a particle next to another particle, next to another particle, if we just think of these as, molecules of air or something like that, then if we think about this, we could say, well, without worrying about the deterministic, like how these things interact with each other, we can, what statistical mechanics does is it says, let's just pretend like it's all random. And as long as we get the statistics to match what you'd expect from the deterministic, then we don't have to worry about all the precise details and positions and velocities. And so if you just have these molecules out here, you'd say, well, it's equally likely that this molecule on the end will move to the right, up, or down. And so I could imagine then at some time in the future, this little aggregate is not going to look like that. These four that are locked over there on the side might still be there, but this other molecule will be over here. It has moved over. And so at this point, we can say, well, it could move back to where it was. But now that it's over here, it could still move down, right, or up. So now it's equally likely to go somewhere else. And so there's like 1/4 chance that it goes back to this clumped shape. But there's a 3/4 chance that it just keeps getting more spread out. And that's just the statistics of it. There's no magic behind it or whatever. It's just that if you were in a particularly ordered configuration and you jiggle it a little bit, then there's a chance that you're going to become disordered. And once you become a little disordered, if you jiggle it a little bit, there's a better chance that you're going to become even more disordered, then go back to being ordered. So it's just kind of a statistical certainty. And that's really what the second law is all about. It's that if we think about the things that make up our world at the very, very small scale as being modeled as if they could just be moving around randomly, then we should expect that without any effort, you can, any sort of things that are in clustered or ordered configurations will tend to become disordered without putting any effort into them. And then if you need to get things back into that position, you're forced to sort of actually exert effort into putting them back into there. But you always are fighting this statistical tendency to diffuse. And that's kind of what the second law is sort of all about. So it's less about generating heat and more about generating disorder, taking things that are clumpy and rich in terms of their structure and breaking their structure down. So eventually, one possible outcome of the universe is that everywhere in the universe, it's just going to be, there's going to be no way to tell what anything came from, because it's just like, if you had some object like a cookie that was sitting on this table, if you just let that cookie sit there forever, then that cookie eventually will just become crumbs and dust on the floor. And you'll never be able to tell from that dust on the floor that it was originally a cookie. And that's kind of the heat death of the universe. Just crumbs and dust spread out over all the space. point where you'll never actually be able to tell what anything actually was, because it's lost all of its structure, it's all its order over time. We'll sort of maybe get to that, but that's a good question. It's not about the generation of heat, it's about the natural tendency for things that were structured to become unstructured. So any thoughts about that or comments about that, or any other reflections people had from that? Yeah.
Well, the laws of thermodynamics apply to like enclosed systems, right? So how, I feel like that'd be kind of rare to encounter a system that perfectly is applicable to the laws of thermodynamics.
Well, so what I mean by closed system is a system where you haven't added any energy to. And so, and it's sometimes it's hard to sort of say, you know, under what time scales can I consider the system to be closed? So the sun is always shining on the earth. So the earth isn't a closed system, it's an open system. And the energy it's getting from the sun is the reason why we have life. That's the whole reason that we have any structure on this planet, is that we have energy from the sun and a little bit of energy that is coming up from the core of the earth. And so, but if you consider the solar system, there's very little energy coming into the solar system from outside. So we can approximate that as a closed system. If I consider an insulated box, like a refrigerator, when the refrigerator's off, the inside of the box we can approximate is not having any energy coming into it. So, so you have to kind of think about what are the fluxes, where is the energy coming from, and the point of the second law is if you don't have an appreciable amount of effort that's being used to hold a system together, then it will just naturally drift apart. Any other comments or questions? Yeah.
I had another question when it talked about Maxwell's demon, and then they started talking about memory and how it it doesn't take energy to record information, but it does take energy to erase it. Why would Maxwell's demon have erased information?
That's a good question. Does anybody have a possible answer to that? Anybody have thoughts about that? Why does Maxwell's demon have to eventually erase its memory to do its job?
Is it just because there's so much information that he'd have to erase it?
Well, yeah, but go ahead.
Well, I think the idea is to have the ability to recognize, I don't know, particles as like high entropy or low entropy. You have to, at some point, have erased memory so that there is like something to learn. Because otherwise, you can't just like exist and then like learn something. You have to have like a base level to erase it first and then learn.
Well, I mean, I would say that I think that's an interesting point. What I would sort of think about is like if you think simpler, like Maxwell's demon is like a bouncer in a bar or something like that. You know, there's a door and they're saying like, you look too young, you know, you look old enough or whatever. And then then gradually it sorts. Because everybody wants to be in the bar, but isn't quite, reach the right age. They're outside, everybody wants to, is inside. But the same with particles. It's like if you're running it fast, then we say, well, fast particles I let through. If you're coming at me slow from the other side, slow particles I let through, and then gradually get all the slow ones over here, and the fast ones over here. But a bouncer at a bar, to me, remembers, like, in order for you to consider the next person, you had to make a decision about the previous person. And as you move to your decision with the next person, you wipe away whatever information you were using to make the decision about the previous person. So if you look at, for example, the state of the door in Maxwell's demon, whether it's open or closed, that actually gives you information about the previous particle. Like if the door was open, then the previous particle that Maxwell's demon saw was either a fast particle moving one way or a slow particle coming in the other way. If the door is closed, then Maxwell's demon knew that for the previous particle that it was the wrong direction. It was a fast particle moving the wrong way or a slow particle moving the wrong way. So every time Maxwell's demon has to make a decision, it sort of loses information about the previous decision. And that's kind of the point of this erasure is that like, and this happens in any calculation, like in a computer or whatever, it's like if you want to make a decision, so your next decision is going to be either 1 or 0, yes or no. And so you've got sort of a space where you're going to put that decision. But that space used to have something else in it. And that it might have been a 1, it might have been a 0, it could have been a Y, it could have been an N. And until you make your new decision, then that memory of the previous decision is still there. But at the instant you make a new decision and you decide it's going to be a 0, all memory of the past decision goes away. And whenever you lose memory of the past, that's referred to as an irreversible operation. And whenever you have an irreversible operation like that, then you've effectively, one way to view it is you've made the system more ordered. Because it's like, regardless of what the previous state was going to be, based on our new information, we are forcing it to be 0. So in the past, we don't know that, like, if this is the bouncer or the bar or whatever, this person's age is independent of this person's age. So when you're making this decision about age, then the previous state of the system could have been either in a previous, age was too young or too old, or too young or old, or whatever the thing was. But the point is, you had memory about the previous thing. And now you forced it and said, for this new decision, we're enforcing it saying, no, this person is too young to go into the bar, and so we're not letting them in. And you've now collapsed the system onto a more ordered state where now you know that for this person, they're too young. And whereas you might have, because you've now forced the system to become more ordered, then that means that somewhere else in the system, something's gotten hotter. And that's a weird thing, but you can measure it in a laboratory. You can go down like near absolute 0, and you can do a calculation that requires discarding a bit of information. What I mean by that is, like, if you have a multi-step calculation, like if you want to add 1 plus 2 plus 5, you might add 1 and 2 together to get 3. Then you might add 3 and 5 together to get 8. Well, when you add 3 and 5 together to get 8, that might cause you to forget this previous calculation. And you can actually measure that there is a little bit of heat that is lost. So there is a little bit of disorder. Other molecules in this system jiggle a little bit more whenever there is something lost. And that's what we mean by erasure.
What about like information storage?
Absolutely, that same thing happens. So like in a computer, if I were to store, if I were to store 3, in a variable, so I'm going to say that some variable in a computer gets 3, and then later I decide in that same variable that I'm going to instead erase that and store 5. Then at the instant you write that new number, then the computer actually loses a little bit of heat.
But couldn't you just like create a new variable and keep the other variable in storage?
You could, but the new variable had a previous value too that has now been erased. So that's kind of the Maxwell's demon thing. It's eventually, that's why they said eventually it would have to erase something because it had to have finite memory. So long as you can, if you could remember every single thing since the beginning of the universe, then this would not have to happen. But because any physically instantiated memory is going to be finite, eventually you're going to have to erase something. But the instant you lose information, then it guarantees that it's going to create a little bit of heat in the system that you're embedded in. So Maxwell's demon doesn't, it effectively creates, an ice box. It creates sort of a hot area and a cold area. But the demon itself at the same time actually gets a little hotter, or the demon itself releases a little bit of heat into the environment. And that's actually happens in your refrigerator. So like a refrigerator, You know, if you've ever looked on the back of a refrigerator, there are all these coils. And so as a refrigerator gets cold, it actually pumps its heat out so that the back of the refrigerator gets hot. And in an ideal world, the amount of heat removed from the inside of the refrigerator would be added to the outside of the refrigerator. It'd be a perfect balance. And that's almost like Maxwell's demon, because that's almost like the sorting process where you're going to make everything slow here and fast here. But what actually happens in your refrigerator is that you get additional heat from the process itself. And some of that we can put our finger on as like, oh, well, there's resistance of wires or something in there. Like there's just extra waste elements that this process that in the ideal process, we just move all this heat over, but realistically, we have to build the thing and there's just extra waste products that go on in the operation of this. And that's one of the things that corresponds to this entropy. So, and this is an important result because when you sort the heat so that it's cold here and hot there, in theory, you're actually creating order in the room because now you're saying that I know that everything in this box is going to have a very slow velocity. That's what temperature is, by the way. It's the average velocity of particles. So everything in here is going to have a slow average velocity, and everything in the back here is going to have a high average velocity. So it seems like I've now ordered my system and lowered the entropy. But in reality, if I zoom out enough, if it's not my whole house, it might actually need to include the power station. But the point is, the process that did this actually generates additional waste, and the waste that it generates will be larger than the order that it produces. And that's the second law there. That's like when you're pushing the block, some of your energy goes into pushing the block, but the other energy just goes into disordering the system. Here, you're creating order, but you're actually creating more disorder outside of the fridge than you're creating order inside the fridge. And that is also kind of relates to Maxwell's. Yeah.
So why did Maxwell believe that there was an entropy increasing outside, that like the demon isn't doing any work?
That's a great question. So, I don't think it's that Maxwell thought that. I think Maxwell posed the demon as a thought experiment to say we don't really understand thermodynamics that well at this point, because in theory I can physically create this like frictionless slider in this being that's able to move it back and forth, and in theory that should just allow, like, I could just set this box down here and not plug it in, like not have any power going into it, and then come back an hour later and all the fast particles be on one side and all the slow particles be on the other side. And what that would mean is one side would be hot and the other side would be cold, which would mean I could use it as a battery. So that would mean that I could have a self-charging battery. And that just doesn't seem right. Like, in order for me to charge up a battery, I should have to be able to put energy into it. So where is the demon's energy coming from? That was really the fundamental question. And this thought problem really sort of said, is there a problem with thermodynamics? And it took decades for them to sort of figure out, like, and it's still controversial today, but this erasure was the thing. When you actually do the math, you can show that the amount of information you need to erase to make these decisions on whether to put the door up or down does balance things out, so that effectively the demon, if this would happen spontaneously, the demon would heat up the rest of the room to such an extent that it would counteract for the order created inside the box. To put it another way, in order to get the demon to create order in the box without heating up the rest of the room, we'd have to plug it into power. So if you power the demon, you can separate these things, and that sort of pushes the entropy generation off somewhere else. But if it spontaneously happened, then it necessarily means that in the vicinity, the entropy had to increase more than it decreased. So, and I don't think Maxwell thought that thermodynamics was fundamentally broken, but I think Maxwell's saying we need to think things through a little bit more. And you know, his little thought experiment is launched, like I said, decades worth of research from other people until it, you know, I think we finally people buy the erasure thing pretty well, but you know, for a while, like, you know, people really just couldn't wrap their heads around it. Even now, the erasure thing is hard to wrap your head around. Yeah.
Still, so how come erasure takes energy, but loading information doesn't? Like that, I feel like that just doesn't really, like,
What
wouldn't,
do you mean by loading?
or not loading, but like processing information, wouldn't that also take energy? Because you'd have to, like in that one with the numbers, wouldn't adding the numbers together require some sort of
Okay, I can give you, so here's an example. So I think the chapter mentioned reversible computing. A little bit, like they mentioned a couple of sentences. This is sometimes called billiard-ball computing. And so, like, colleagues of mine who work in like quantum computing, this is really important to them because if you don't have reversible calculations, then all of the kind of quantum mechanical magic, superposition, and uncertainty, and all that helps you breaks down. Because at the instant you have an irreversible calculation, then this wave function collapses, and you lose all your quantities. And so they worked on this thing called reversible computing, and the billiard ball model is kind of an easy way to think about it. Like, let's say I wanted to calculate. This is a very simple thing, like x and y. And it could be either true or false. And you can say, what's x? Well, let's say x is occurrence of event at time 0, and y is occurrence of another event at time 0. So effectively, if I want to calculate x and y, what I'm really saying is, did these two events happen at the same time? So it doesn't seem that exciting a calculation, but it's my claim that inside a computer, this is just as fundamental as 1 + 1 = 2. And so I say, well, how can I build this in a reversible way? Well, you could imagine putting imagine a kind of a pool table with a ball that can be launched from one side straight across, and I'll have like a hole, a pocket here, and another ball that can be launched straight across with a pocket here. And if only one event happens, then so I'm going to say that if x happens, so whenever the event happens, launch a ball. So launch on x event, and then here we launch on y event. And so if you set these spaces up just right, then if x and y happen at the same time, you'll get a collision right here. And these balls will go off in some direction that is not their pockets, you know, whatever the directions might be. But if x and y do not happen at the same time, so these balls are launched at different times, then in that case, you'll get one ball will land in this pocket, and the other ball will land in this pocket. And so, if you detect that a ball hits the pockets, then you know that the two events didn't happen at the same time. If you instead detect that at a particular time that that balls didn't arrive at their destinations, then you must know that these two events did happen at the same time. So if they hit, you know, over here, then that means that same time. But if they hit here, that means different time. All right, now, the reason I bring this up is that no balls are ever destroyed in this experiment, and no energy is ever lost in this experiment. It's traded among the balls, but the balls themselves, all of the energy is conserved through this. So you put a certain amount of kinetic energy into the balls, they might trade it and go off in these other directions, but and then you could imagine that when they go out this pocket, there's another billiard ball table with another computation. So the people who designed reversible computing have figured out a bunch of these gates, like inside a computer, there's a bunch of these little digital gates, we call them, that are logic gates. And they implement all the type of logic that goes into detecting when I press a key and how to calculate numbers and all those sorts of things. Well, the reversible computing folks have figured out how to build gates out of the equivalent of this billiard ball table, where these balls just keep going from table to table to table. And if you can string enough of these things together, no balls ever disappear and no energy ever changes. They just keep rolling around with whatever kinetic energy they had to start with. And that's an example of how a calculation itself need not generate any entropy. And it conserve all of the energy, all of the internal energy that it had in the system. But at the instant where one of these balls were to disappear and not be carried forth, so if I were to grab one of these balls and take it off the table, I've now lost the history of its trajectory. So all of the information it was carrying about all of these previous steps of the calculation have now disappeared, and I've also taken energy out of the system. And so that loss of internal energy in the system will actually then create an increase in entropy. So basically you're trading the internal energy that wasn't the kinetic energy of these balls for a heat generation outside of the system. And so that's kind of an example. Like a standard way you would do this calculation in a computer is that at the instant you calculated a result, whatever memory was needed here, well, effectively you just discard. Like you might reuse whatever this thing was to generate this, but then this result will be totally discarded, and that would be an erasure. But if you can calculate things using this weird billiard ball setup, you don't actually have to get rid of any balls. You don't actually have to change the energy in the system. You can do the calculation without erasure. It might be a little abstract, but that's why like people didn't actually. I mean, and it says it in the text. Up until they started working with reversible computing, they said, that's how they solved the Maxwell's demon problem. They said calculating things must use energy. And then a decade or so later, after they resolved Maxwell's demon, someone came along and they figured out how to put these billiard ball tables together and do calculations. And when they did that, they realized, wow, we can string together calculations that don't actually change the amount of internal energy in the system. In other words, they don't generate any entropy in the calculation itself. We need to revisit Maxwell's demon. And that's when they came up with erasure being the key. Okay. Any other thoughts or comments about that or other things in the chapter? Okay. Oh, those are good comments there. I mean, the reason why we're looking at these things, because they seem a little abstract, is that when we think about complex adaptive systems, we're going to hear two things over and over again. One, the complex adaptive systems self-organize. They create order, they structure themselves. And in order for us to even start wrapping our heads around that, we need to sort of know, what is, so if you think about complex adaptive systems, they self-organize. And so, that causes us to ask the question, well, what is order and what is disorder? How do we even know if something is organized, let alone self-organized? So that's one thing that causes us to come to this chapter. And the other thing we're going to hear about is that they process information. And we can sort of come up with a hand-wavy explanation for what the heck that might mean. But it would be nice for us to know precisely what is information. And so that's really why these tools end up being useful for us. And then they provide us frameworks that will help us quantify things like the complexity of an ecosystem, for example, and how that complexity is changing over time, and so on and so forth. So questions go beyond the mystery of Maxwell's demon. So that's kind of what we one of the reasons why I want you to read this chapter. The other thing that this chapter does, it introduces us to statistical mechanics. Does anybody remember what mechanics is from the previous chapter? Not statistical, but just classical mechanics. The word mechanics. We said there are two types of mechanics, dynamics and kinematics. It's kind of like how things move. So mechanics is sort of a theory of, or a framework for explaining how things move, how physical objects move. So in chapter 2, all of the mechanics you learned about were deterministic mechanics. They were like Newton's laws. If you have something, you give it enough energy, it moves in this direction until something else hits it. And the only reason it would possibly stop moving is if another force acted upon it, and so on and so forth. You focus on every single small thing and all of how those things interact with each other. Now, statistical mechanics says that's way too hard. We need something that is more practical. And it takes the approach of stochastic instead of deterministic modeling. How many people have heard the word stochastic before? What does stochastic mean, do you think?
Randomness.
So a lot of times it's associated with randomness. So usually if somebody says this behavior is stochastic, it's usually legal to substitute in the word random. Oh, they mean it's random. But there's a nuance there. The word stochastic comes from the Greek for guess or conjecture. And that seems a little weird. You'd expect it to come from the Greek for random or something. And then you wonder, well, why do we have two words for random? A stochastic model is not just purely a random model. A stochastic model is a model in which someone has said, I'm going to guess that the behavior is random, even though it's probably not. So it's someone saying, I don't care if the behavior in the real world is actually random. I'm going to choose to model it as if it were random, because that's going to be easier for me. And this is exactly what happens in board games, for example. So in a board game, you might encounter a dragon or something like that. Now, in the real world, if you were to encounter a dragon, your ability to kill said dragon would be determined by a wide range of things that would be great to depict, like on the silver screen. You might, like you'd be lucky enough to dodge, some fire breathing. You might have to be strong enough to swing this sword. The dragon might have to be a little tired that day. There's all of these things that would go into whether or not you beat the dragon. But in a board game, what do you do when you come up against a dragon? Do you fight the dragon, or in the actual board game, how do you determine if you win against a dragon? Roll a dice, right. Roll dice. And you look at a card, and that card says that if your dice comes up 1 through 4, the dragon won. But in the rare cases, it comes up 5 or 6, you won. And so you have a rare chance. As long as those statistics match, it doesn't matter that we've glossed over all the cool details of how the dragon was fought. All that matters is that with your strategy and its power, you're going to win only 20% of the time. And so we just need to roll dice that come up win 20% of the time. So that that greatly reduces how many details I need to keep track of. And that's what stochastic modeling do, is that it uses randomness to remove variables from models. And so when I say I have a stochastic model, what I'm saying is if I were to replace this with a deterministic model, it would have so many more endogenous and exogenous variables that I would not be able to keep track of. So I'm going to replace it with a random model, and as long as I've got good stats, then in that case, my random model is going to do just as well, but I'm only going to have a couple of variables keeping track of, like, the mean of some distribution, the variance of some distribution, and that's it. And I let the distribution generate the variability for me. That's what a stochastic model is. And that's what statistical mechanics does. It replaces Newtonian mechanics, classical mechanics, with dice rolls. And so we talked about how that led to this picture where if you have a room where you have a bunch of particles clustered, and a little bit later, those particles spread out. I guess I should draw the same number. Then there are more ways to become spread out than there are to become clustered. So more ways to spread than cluster. And so because of that, if you were just randomly moving these things around, then you would expect that regardless of how you started, you're going to end up in a more spread out space. And that suggests to us a new ball and basin model, where the most clustered distributions here are like sitting at the top of hills, and the most spread out distributions are sitting at the bottom of hills. So now as the ball is rolling around the basin, then it's actually describing whole distributions of molecules of air. And so we can talk about some distributions being unstable and some distributions being stable. And that sort of said, well, how do we make sense of that? So that you can say that a clustered distro of molecules or particles is unstable. And a spread out is stable. And what I mean by stable is that if you had a spread out distribution, where this is sort of the extent of all the particles in the room, if you were to think about how each particle moves, there are a bunch of ways for particles to move differently and the spread of the distribution to stay roughly the same. And so there are more opportunities to be spread out than there are to be clustered. And that's what makes this clustered distribution, or sorry, the spread out distribution that it's rarely do you become more clustered. And so if I want to become more clustered, I pretty much have to move things myself, and I have to put energy into it. So without energy, I roll down to the bottom of the hill, and I become clustered. If I push all of the particles up into a corner somewhere, and I expend energy to do that, That's like me rolling that ball up to the top of the hill. And once they're up there though, if I stop putting energy into the system, it rolls back down to the hill again. So it's really like we have a ball and basin model in distributions. So it's like distributions rolling around ball and basin models. All right, so is that conceptualization clear? Do you see what I mean by that? And so we kind of, this is our sense that we need something that sort of like quantifies this idea. What does it mean to be, why is this distribution? How can we spot when a distribution is going to be stable? And how do we quantify that? How do we look at a configuration of the world and say, that thing is somehow robust to random variation? I'm not going to need to constantly put energy into that thing to keep it where it is. And that gets us into these things like microstates, macrostates, and this idea of entropy. And so in StatMech, we have a notion of a microstate, and that is a fine scale configuration of a system. So this is like the positions and velocities of all particles in a room. And so one microstate is like, a microstate doesn't correspond to a particle, it corresponds to all of them at once. Like you're all sitting in a particular spot, that's a microstate. If one of you moved into a different chair, that would be another microstate. So it is the configuration of the individual elements in the system. Each configuration is what they call a microstate. Now, we can say there are certain configurations that have properties, and those properties are called macrostates. So this is a coarse scale or coarse grain property of microstates. So, for example, we could talk about, and sometimes these are called equations of state, or functions of state. And so the idea is that a macrostate is going to map, it sort of is a map of many microstates to one property value. And so like, if I look at all of you, I can say, what's the number of students in the class right now? That could be a macrostate. So number of students is an example. Or I could talk about what's the average space between students. So that's another macrostate. I could talk about the density of air molecules. I could talk about their pressure. I could talk about the temperature, which again is related to the average velocity of molecules. These are all macrostates. And so the idea here is I could say, if there's 14 students in the class, there are a wide range of different ways those 14 students could be sitting in seats. That's what I mean by it's mapping multiple microstates to one macrostate. The macrostate is 14. The microstate is any way 14 students could sit in these chairs. But I could say, well, the average space in between students is 1 meter. Well, I can now say, well, of all the different ways that students can sit in this class, there's only a small set of them are going to have an average space of 1 meter between them. So that might be a smaller set of microstates. So we identify a property and we ask how many microstates have that property. That's how we get from microstate to macrostate. Are there questions about that? So we can count the number of microstates in a macrostate. No questions about that? This, by the way, is creating, this is what we call multi-scale modeling. You can model things in the small, you can also model properties in the large, and going from that one direction to the other, this is what we call coarse graining. And so a lot of times in systems, we'll recognize that there's just way too many parts. But we notice patterns seem to occur. And we say, wouldn't it be nice if we could come up with a coarse graining of this system so that we can just describe things at the macrostate level and forget about all of the ugliness happening in the microstate level? That's what coarse graining is. Yeah.
So would that be in the opposite direction, or is that from the microstate to the
It's
macrostate?
from the micro to the macro.
Oh, okay.
So it's fine scaled and this is coarse grain. Fine grain is coarse grain.
Like weather stations, you can like use that to put it over an area.
Yeah, right. I mean, there's a lot of different ways right. Any way you can take a high degree of freedom system and come up with some property that allows you to think about it as a lower degree of freedom system. That's of course. Yeah.
It reminds me a lot of just like the difference between microeconomics and macro.
It's exactly that. Yes. These properties applied to economics is the difference between microeconomics and macroeconomics. So GDP is a macro state of the whole economy. There are a bunch of different ways to hit a particular GDP. And what the people at the Fed do is they look at, they have to live in both worlds. So the Federal Reserve knows that the whole economy is driven by interactions of the microstate. They have to come up with interventions that drive the micro world that hopefully cause the macro indicators to move in the direction that they would like. And if we have a total theory of macro stuff, like it might be that we can start kind of like in the case of heat and temperature, we generally know that if one thing is hot or if one temperature and another thing is another temperature and you put them next to each other, then over time, the temperature of one box will decrease, the temperature of the other box will increase. And so at that point, we can describe the whole system just in terms of its macro variables. Now, the economy may not be as nice and tidy as a thermodynamical system. And so that's why in the Fed, they probably have to think about both of those. And that's the reason why we have microeconomics. We're talking about supply and demand. All the individuals are bouncing around, they're bartering for things and deciding on prices. That's micro scale. If we zoom out, we'd say how much total effort, how much total productivity is in an economy. That is a macro variable. Great connection. All right. Any other comments or questions about that? All right, so now that we have this, and by the way, I guess I should add this term. This counts, by the way. We use a term for that. And that term is multiplicity. So we can say that a particular macrostate has a higher multiplicity than another macrostate. That's just a term that we use for the count of the number of microstates in a macrostate. All right, so then that leads us to finally taking something that was very qualitative in the past, and what Boltzmann did is define Boltzmann entropy. And Boltzmann entropy was basically just, it's defined as S is the letter we use for it. And it's just this is a coefficient, Boltzmann's coefficient. It's just something to help make the units work when Boltzmann's entropy is introduced into physical equations. It doesn't matter, it's just a proportionality coefficient. The important thing that matters is then the natural log of the number of states. So this is the multiplicity of a macrostate. This is the number of states in a number of microstates in a macrostate. And this here is the entropy of a macrostate. And the important things to remember here is that as the number of microstates goes up, entropy goes up. So it doesn't matter that much that there's a natural logarithm. The reason the natural log is in there is because Boltzmann wanted a convenient quantity that made entropy additive. So it's kind of like if you have two systems, so you have system A, and it's in macrostate X, and then you've got system B is in macrostate Y. Well, you know that in macrostate X, there's, let's say, in X microstates. And in macrostate, or in system B, there's in Y microstates. So if you were to combine these systems together, then together, the new AB or XY macrostate has in X times in Y microstates. In other words, if we know we're in macrostate X, we don't know what microstate we're in. It could be any one of these. If we know that this system is in microstate Y, we don't know which of these it's in. It could be any of these. So when you put these two systems together, like this classroom, I know there's 14 students. The classroom over there, I know there's 15 students. I don't know with that information, where the students are sitting in either classroom. If for some reason I now need to know about both classrooms simultaneously, I now have to consider how many different ways you collectively can sit in both classrooms. Well, that's going to be all the ways you can sit in this classroom times all the ways you can sit in that classroom. Well, what Boltzmann wanted is a way that when you add up these two things together, you get additive entropies. And he said, you know what? If I use the logarithm, it all works out. Because log in X in Y it doesn't matter what base, is equal to log in X plus log in Y. And because of that, the entropy XY is equal to the entropy of X plus the entropy of Y. That's the only reason that Boltzmann used log here. And he used the natural log because it was convenient for some of the physics that uses entropy. It doesn't matter what logarithm. He just picked a log and a proportionality constant to make it work. But the important thing here is it's just a logarithm of the number of states, and that allows this magic to work out. And that's how we got Boltzmann's entropy. And I want to pick up from there next time and then see how this brings us to information entropy, and then talk about things like how this applies to hurricanes and living systems and biodiversity and other sorts of things. So that's where we're going with that. So if you have any questions, I'm happy to take them after, but in the meanwhile, I don't want to keep you too long. So the attendance exercise here, how about we say, what is another word? What is a one-word phrase for the number of microstates in a macrostate? So one word, not a one-word phrase, just a single word. What is a single word we can use that represents the number of microstates in a macrostate? It's not entropy. It's another word that's just a count. So the entropy is kind of a logarithm of this count. So what's the word we use for the number of microstates in a macrostate? Otherwise, we'll see you Thursday. Stay dry, stay warm.